All right, folks, we're back. This is section 3 of Unit 4 of AP Calculus, rates of change in applied contexts other than motion. We're going to talk about some of the basics of how these problems look, and then we're going to do a ton of examples. It's probably going to take me a couple videos to get through all of the examples that I have for you in this lesson. So let's go ahead and get started. So what we're going to do is we're going to look at rates of change in a variety of other contexts other than straight line motion. Like straight line motion kind of stands out as the number one way that we see rates of change in applied context, and then we have, other types of problems involving rates of change. I say here these problems are almost always calculator active problems, so you want to make sure you have your calculator ready for this lesson, because we're going to use our calculator on every single problem that you see today. And a lot of these are sampled from old AP exams, or more recent AP exams. There's a lot of examples of parts of problems that show up in AP exams. So, all right. You can see here a rate function helps us to predict how some quantity will change over the course of time. When's the quantity increasing? When's the quantity decreasing? How fast is the quantity increasing or decreasing? Those are all things that rate functions will help us answer the question to. A rate function is the derivative of some original function. If we have a function for the total number or total amount of something, then the derivative of that is going to be my rate function for the original function. Notice that I say here, this doesn't necessarily mean that the rate function will be written as a derivative. Sometimes the problem will state that a function like q of t is the rate of something. So sometimes you're given a function for the total amount, sometimes you're given a function for the rate. You need to be aware of which one you're dealing with. When you're given a function with the total amount and supposed to find the rate, you need to take the derivative. If you're given a function where it is the rate, then you don't need to take the derivative in order to find the rate of that particular whatever it is. And on your AP exam, the rate function could be given as an equation, a graph, or a table in any given problem. So we can see all three of those modalities. Typically on your AP exam, they expect you to do one of the following things. Find or approximate the derivative of the rate, which is actually finding the second derivative of the original function. Interpreting a derivative or second derivative value in context using appropriate units. Determining when a quantity is increasing or decreasing based on the given rate function. So those are all things that they might expect us to do. And then if we have some function a of t, that's the function of some quantity, and a prime of t represents its rate, then the following relationships all hold and can be useful to us to use in various problems. If a prime of t is greater than 0, that means that a of t is increasing. So if a prime of t is positive, a of t is increasing. If a prime of t is negative, then a of t is decreasing. And if a prime of t is equal to 0, then that means that at that moment a of t is not changing. So let's go ahead and we'll dive into the examples that we have and see how far we can get. All right, example number 1 from the 2002 AP Calculus Exam Form B, free response question number 2. This is a calculator active question. The number of gallons P of t of a pollutant in a lake changes at the rate P prime of t equals 1 minus 3e to the negative 0.2 square root of t gallons per day, where t is measured in days. Is the amount of pollutant increasing at time t equals 9? Why or why not? So since we have a rate function here already, we don't need to take the derivative of anything. Since we have a rate function, if we want to determine if the amount of pollutant is increasing at time t equals 9, we're looking for when the rate function is positive. So we want to find the value of p prime at 9 and see if that's positive or not. If it's positive, then the amount of pollutant is increasing. If it's negative, then the amount of pollutant is not increasing. And this is the point at which I'm going to turn to my calculator and so I'm going to go ahead and punch this function in, substituting. I can never find E on these. There we go. Substituting in the value that we have for t, which is 9, And I'm going to go ahead and we get negative 0.646. We want to, of course, round or truncate to at least 3 decimal places. So we've got negative 0.646 for our rate function. We could give units to this. In fact, maybe we should. These are measured in gallons per day. So, is the amount of pollutant increasing at time t equals 9? No. The amount of pollutant is not increasing. It's not increasing because p prime of 9 is less than 0. Not increasing at time t equals 9. Okay. All right. Example 2 from the 2004 AP Calculus exam, Form B, free response number 2. Again, this is a calculator active question. For time 0 to 31, the rate of change of the number of mosquitoes on tropical island at time t days is modeled by r of t equals 5 square root of t cosine of the quantity t over 5 mosquitoes per day. Part A, show that the number of mosquitoes is increasing at time t equals 6. Okay, so that means I want to show that the rate of change of the number of mosquitoes is positive. The rate of change is given by this function r of t. So all I need to do here is substitute 6 in there for t. That becomes 5 root 6 cosine of 6 over 5. And go ahead and calculate that out. So we got 5 root 6 times cosine of 6 over 5. And we get 4.438. 4.437 also acceptable. And our units here are going to be mosquitoes per day. Okay, show that the number of mosquitoes is increasing. Since the rate of change of the number of mosquitoes is positive, mosquitoes is positive at t equals 6. This means that the number of mosquitoes is increasing. All right. Next, part B. At time t equals 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Give a reason for your answer. Now, this is, since we're looking at whether the number of mosquitoes is increasing at an increasing rate, we're actually looking for the rate of the rate here, which means we are looking for the derivative at time 6. Okay, now, I totally could take the derivative of this function using the rules that I know for taking derivatives by hand. However, since this is a calculator problem, I would never in a million years recommend that you take the derivative by hand. Whenever you have a calculator in your hand and they ask you to find the value of a derivative of something at a point, you should use that calculator. So I'm going to go to my calculator here, and I'm going to set up my numerical derivative. There's my n deriv of 5 square root of, and my calculator will put x in there instead of t. And I'm certainly not going to change the mode to have my calculator put t in there. With respect to x at time 6. For those of you who have newer calculators, my apologies that my technology is old and shoddy. What did I do? Uh-oh, I lost my cosine. Cosine. 5 root x cosine of. There we go. Oh. Now I have an extra parenthesis. This is what happens when you're punching stuff into your calculator. There we go, finally. And we end up with negative 1.913 as our value. So the number of mosquitoes is increasing at a decreasing rate at time t equals 6, since the rate of change of the rate of change is negative. Since the rate of change of the rate of change is negative. All right, let's see. Can we get one more example in? Let's go on. Example 3 from the 2007 AP Calculus Exam Form B, free response number 3. The wind chill is the temperature in degrees Fahrenheit a human feels based on the air temperature in degrees Fahrenheit and the wind velocity v in miles per hour. If the air temperature is 32 degrees Fahrenheit, then the wind chill is given by W of v equals 55.6 minus 22.1 v to the 0.16 and is valid for v between 5 and 60. Find W prime of 20. Okay, so again, this is a calculator active problem. So I'm going to go ahead and use my numerical derivative again. So I'm going to go to Math 8 and punch in my function, 55.6 minus 22.1 x to the 0.16 with respect to x at 20. I hope I typed all of that in okay. And we get negative 0.286, negative 0.285 acceptable. We can truncate there instead of rounding. And explain the meaning of W prime of t in terms of the wind chill. So at v equals 20 miles per hour, the wind chill is decreasing, and this is where it gets tricky, at a rate of, and now I need my units to be correct, a rate of 0.286 degrees Fahrenheit per, and this variable, the 20, is not a time value, it is a temperature, or it is a wind speed value per mile per hour of wind speed. All right, and there's our explanation. All right, that's all we're going to have time for in today's video. Come back, or in this video, not today's video. Come back next time for more examples of example AP problems where we're applying rates of change in contexts other than motion. All right, see you then. Have a great rest of your day.